Copenhagen, and he's Anton Mallasto, and he will talk about the formalization of the natural gradient method for general similarity measure.
Thanks for the introduction. So just the first disclaimer, if there are any information geometers in the audience, this might seem very trivial for you. But I think from the optimization perspective, it's very important that we kind of say these things aloud that we have here. Right. So here's the agenda for the talk. We will start by reviewing what a statistical manifold is, then look at what the natural gradient is, and then look at our formulation of that for general similarity measures. So statistical manifold is a triple of X, a sample space, theta, a parameter space, and a rho that is a map from the parameter space to the set of probability densities over the sample space X. So visually, you have the parameter theta, and through rho, you map it into the density there, and this density can just be viewed as a point on this manifold of probability measures. And then usually what we want to do when we're carrying out learning is to minimize some kind of similarity measure between probability distributions. So what we do is that we give the statistical manifold a similarity measure C star between rho theta and some rho theta prime. But note that the similarity measure here can also be applied to a point that is outside of that manifold there, because this manifold that you see here is just the one that you get from this chart given by rho. But there might be some kind of probability measure here that is not covered by the manifold. But let's say that the rho theta here is the projection of that for now under this similarity measure. And then what we regard from that similarity measure is that it's positive definite. So it's zero only if rho and rho prime are the same, and then it's strictly convex in rho. Then what we do usually is that we pull back the similarity measure from the manifold to the parameter space by defining that the similarity measure between a parameter and rho is given by the similarity measure between rho theta and rho. And finally, we will just assume for a technical detail that the similarity measure between two parameters should be C2 whenever theta is not the same as theta prime. But when theta is theta prime, then it should still be twice differentiable. It just doesn't have to be continuous, the differential. Right. So usually when we optimize such a similarity measure, we do it by gradient descent. So at each step, we take our current guess for the parameter and update it with some learning rate times the negative gradient given here. Now, usually when we compute the gradient, we just compute the vanilla gradient with respect to the Euclidean metric, whose direction can be characterized as this. So we want to minimize this expression with respect to some vector v, where v is constrained to lie inside a sphere here, or on a sphere. And then as the radius of the sphere goes to 0, we get the gradient direction. And then what we usually want to do is that instead of the Euclidean metric here, we want to replace it with some kind of metric that takes into account the similarity measure on the space of probability measures that we're using. And this is kind of the main idea behind the natural gradient. So here, just a brief illustration. So our problem is that we're given this trust region here with radius delta, and the theta 0 here is our current estimate. And then we want to find our way eventually to the minimum of this contours. So what we do is we find the minimum from this trust region, and then if we kind of vary the trust region and let it go to 0, we get this path, and the path here has the gradient as its tangent. But do note that if we actually change how our unit spheres look or how our spheres look, then we will get a different gradient here. And this is the entire point behind why Riemannian gradients are different from just vanilla Euclidean gradients. So what we want to do is that we want to give the parameter space theta a Riemannian metric, g theta, where we denote the metric tensor as capital G, and then the distance we denote by d theta. Then at any point, the Riemannian gradient is given by this expression. So what we do is that we compute just the Euclidean gradient here, but we have to precondition the gradient with the inverse of the metric tensor at that point. And that gives us the natural Riemannian gradient. Another way how we can view this is in the same formulation as above with the visualizations, where we kind of just keep shrinking the trust region. So if we take the metric tensor to be the Fischer-Rao metric, then we get what most commonly is known as the natural gradient, at least in machine learning and optimization, where usually you're trying to maximize the likelihood of your model. So, and there people have noticed that the Fischer-Rao metric gives you very stable gradients to maximize the likelihood. If we instead choose this metric tensor to be the Hessian of our objective function, then we just get the Newton's method. But we have some trouble here because Fischer-Rao metric might not always relate so well to our objective function, and the Hessian it's not always that easy to compute it. So what we're going to do instead is to define the formal natural gradient that takes the similarity measure into account through a local Hessian. So it's essentially, yeah, it's the Hessian, but we kind of look at it at a very local scale. So here we wrote the Riemannian gradient as a solution to this minimization problem, this trust region problem. If we replace the Riemannian distance here with the cost c, then we get this solution here, where this H matrix here is the local Hessian. And we will now derive that. Yeah, and this here is what we call the formal natural gradient. But we could also just call it the natural gradient. So we start with the problem formulation, and then we do some easy approximations. So we approximate the trust region condition in a quadratic manner, and then the objective function, we approximate it with the first degree Taylor expansion. Then we write the Lagrangian for this constraint problem. And then when we take the gradient and let it be 0, then we get the formal natural gradient. So kind of here is a small observation between the connection between different optimization problems. We start with the trust region formulation, and through the Lagrangian formulation, we get a proximal formulation. And finally, when we approximate the proximal formulation with these Taylor polynomials, we arrive at the natural gradient. And in our paper, we have further discussed these different connections that have been in the literature. And in the community of information geometers, they call this local Hessian as the Riemannian metric associated with the divergence C. And here's just a technical note. We use this limit here instead of just assigning that eta should be the same as theta, because C doesn't have to be, or the Hessian of the C doesn't have to be continuous at eta. And in the Riemannian case, where C is some distance function induced by a Riemannian metric, we don't have to worry about anything here. But if this similarity measure here is, for example, a distance induced by a Finch-Silleria metric, then this won't be continuous and we have to take a limit from some direction. And then just for convenience's sake, we're going to take the direction from the negative gradient. And here's an easy proposition to show that asymptotically our method will just be the Newton's method, which is also known in the natural gradient case, because there it's well known already that if you're maximizing the likelihood, then the Fischer-Rao natural gradient will asymptotically just be the Newton's method. And then now that we have derived what we call the formal natural gradient, we will just give some examples. So if the similarity measure is given by an F divergence defined here, so we pick a convex function F that has to be 0 at 1. Then this is how you define the F divergence. Then when we compute the local Hessian for that, we get this solution. And if you look closely, then this expression here is the Fischer-Rao metric tensor. We just get this scalar in front here, which is the second differential of f at 1. So if you compute that in the case where f equals minus of log, then the f divergence will just be the Kullback-Leibler divergence. And this local Hessian here will just be the Fischer-Rao metric tensor. So this is a generalization of the natural gradient in that sense. Now for another example, let's consider a Finch-Silleria metric. So choose a Finch-Silleria manifold with the Finch-Silleria metric f that satisfies being strongly convex. So if you look at the Hessian of the metric, then it should be strictly positive definite outside of origo. It should be positively one homogeneous. Essentially, this just means that if you have a positive scalar inside, you can take it outside. And then it also has to be positive definite. So it's always positive except when V is at the origo. Then this metric induces a distance on the manifold that is given by this expression, which you minimize with respect to a curve gamma that has to be continuous and connects this rho and rho prime together. Now, if we want to look for the natural gradient in this Finch-Silleria case, we again have to compute the local Hessian first. Right. But before that, we define the fundamental tensor here, which is just the Hessian of G at V. And because this fundamental tensor is now the second derivative of a zero homogeneous function, no, sorry, it's the second derivative of a two homogeneous function, and that's why it's a zero homogeneous itself. And it's also positive definite, so then it induces a nice metric that we can use. Then when we compute the actual local Hessian, we get this expression. So here is U defined. U is just the gradient direction that we used before. So here we essentially get a Riemannian metric that depends on the direction in the tangent space. So when you're in tangent space and you move around, also the metric tensor changes. And if the Finsler metric is just a Riemannian metric, then this fundamental tensor here will just be your Riemannian metric tensor. A nice special case of Finslerian metrics is given by the P Wasserstein metrics defined on the manifold of probability measures. The P Wasserstein metric is defined by this optimal transport problem, where you are looking for the joint distributions with first marginal rho and second marginal rho prime, and then you want to minimize the expectation of the p-th power of the distance function. And then it has been shown by Marshall-Ague that this actually corresponds or is induced by a Finslerian metric given by this expression here. So here you have to notice that when you take the Finslerian metric at V, it acts through this phi function here, where this phi function has to satisfy the continuity equation, where rho x is the point on the manifold where we're working, or whose tangent space we're working in. So then when we compute the fundamental tensor, that also is the local Hessian in that case, we get this quite nasty expression here. But in the special case, when p equals 2, this term here will disappear. This term will also disappear. This will be just 1, and this will also just be 1. And in the end, you just get the inner product between these vector fields. And when we run a simple toy example where we use these formal natural gradients, we wanted to maximize the prior likelihood of a Gaussian process model in Gaussian process regression. So we have this data set given by these black dots, and then we want to fit this Gaussian process. So when we use different natural gradients, you notice that the Fischer-Rao natural gradient converges fastest. And that is kind of to be expected because you're just maximizing the likelihood here, which just means that you're minimizing the KL divergence. So then the local Hessian of the KL divergence is given by the Fischer-Rao metric. Yeah. And then here are just some references for the paper from Ague, where they show that the P Wasserstein metric is induced by a Finslerian structure, Amaris paper on natural gradients, and then there's two papers by Yifan Chen and Wushen Li, also from Wushen Li and Guido Montefar, on the natural gradient, on the Wasserstein natural gradient, which we got here when we just make p equal 2. And then finally, there's a reference for discussion on the Riemannian metric associated with a divergence. And with that, I want to conclude. Thank you.
Can you go to Formula 4?
Sure. Oh, was it there?
So my question is, the sphere that you define, the ball, is based on the cost function.
Yes.
So the Hessian that you have, I mean, the metric is the Hessian.
No, it's not the Hessian, it's the local Hessian.
What is the difference?
So the difference is, let's find the Hessian. So in the Hessian case, the other parameter here is rho. So you have the distance between 2 points, and then you want to approximate the distance when you start moving from here to here. But in the local Hessian case, you're looking at how the distance works around the point where you're moving, if that makes sense.
So isn't the Haitian a local notion?
The Haitian is a local approximation to the distance between the 2 points. But our local Haitian instead just works around 1 point. So the Haitian needs 2 points, but the local Haitian just needs 1 point. So it's just, essentially it's just, you have the you have the divergence, then the local Haitian is just a Riemannian approximation to that divergence.
Then I have another question. So the notion of natural gradient brings invariance to the parameterization of the model. In your formal natural gradient, you lose this, right?
No, because the local Hessian also depends on the parameterization you're using. Right. So just like in the Riemannian case, I mean, the kind of the invariance to the parameterization comes from the optimization problem you're having when you have the trust region optimization problem. So no matter what kind of parameterization you have, you're still working in the same set. And you still find the same minimum for that optimization problem, no matter what your parameterization is. So of course the representation will be different based on the parameterization you're using, but the kind of actual direction will be the same.
Other question or comments? We have time as we do the speaker.
Thank you.